Welcome. My name is Greg Alton. My colleague David Bates and I wish to share with you a unique filter we have been investigating to meet the special challenges of the highly integrated RF front ends we see today in the 5G market. So we have titled our discussion to match this concept, a panelized filter array for millimeter wave 5G applications. We'll review a little bit of history, discuss some applications, then introduce our recent research. Although the Knowles name is newer, many of you will recognize that our Dielectric Laboratories brand, or DLI, has been in the industry for more than 4 decades. Our start in microwaves came with the introduction of our single layer capacitor in 1974. After 20 years of growing that business, we began to see significant changes in the market and technology space. Changes that allowed more integrated and compact assemblies using surface mount technology. An application for us at the time was to support customers building phased arrays in the plank brick architecture style. Only 6 years later, Knowles DLI designed, manufactured, and qualified KU band filters for the Mars rover Curiosity. And in the last decade, Knowles DLI has followed the trends into complete SMD assemblies through multiple projects and to microwave frequencies that support the FR2 band of 5G communications. As we look to 5G deployment, we look at small cells for most microwave applications. And thanks for the technology that we've already discussed, these are incredibly dense units. So size, weight, power, thermal, and cost make up the equation for how our cellular backhaul is going to roll out in the coming few years in microwave frequencies. Our experience at Knowles DLI in both commercial and military markets has given us a lot of insight to the swap and swap C challenges that our customers are facing. So we've been looking at ways to innovate our technology to make sense for these people who are working at microwaves in very dense packages. Before we get too far into our proposed solution, let's look at the background need. RF systems use filters to mitigate spurious signals, meet interference compliance, and minimize system noise. In phased array architecture, which most 5G millimeter wave systems are using, there are 3 filter positions to consider. Position 1 is behind or in combination with the antenna. Position 2 is behind the first amplifier, and position 3 is between the mixer and the feed network. Most applications we see choose to put a filter at position 3. Designs mindful of swap C can use one filter for every 8 or 16 when using a position 3 filter, saving themselves integration expense and the cost of multiple components. For some applications, having a filter at position 1 is actually crucial. It's the position where interference suppression has the biggest payback in supporting system performance. But position 1 is technically challenging and demanding. It requires high Q and low loss in a small space, and essentially direct one-to-one integration with each antenna in the array. Achieving all those goals is very difficult to achieve in panel form phased arrays. Challenging enough that many designers have given up looking for filter solutions at position 1, while others have given compromise to be able to integrate such a design. Let's now have a look at some current filter technology. Here is a comparison of surface mount and board integrated filter technologies common to 5G FR2 systems. The different build technologies of microstrip, stripline, and Knowles DLI thin film ceramics show differences in the response, yet are comparable. The Knowles DLI filter is able to achieve a steeper rejection slope on the high side of the passband in this design. But more significantly, that filter shown in blue is a fraction of the size of the other options. Since it's also a discrete and tested component, a board or system designer can mitigate significant risk in manufacturing yield due to the effects of board fabrication tolerances in millimeter wave systems. The surface mount integration, size, and performance are all features of the ceramics and thin film technology that the DLI brand has been advancing through the organization's history we discussed earlier. Now, I'll turn this discussion over on advancing filter technology to my colleague, a Knowles Fellow, David Bates.
Thank you, Greg. Hello, I'm David. The ghost of IMS conferences passed. Well, not really, but I do wish you all much health this year. I know this is an unusual time for us all. But on with the show. This slide shows two of the primary array constructs that are used throughout our industry. First on the left is typical of high-performance military arrays. And you see the radiating elements here represented by square patches on the front face and TR modules oriented 90 degrees protruding behind. So in this configuration, the TR module length is arbitrary and allows for greater area for the circuitry, which enables those higher performance arrays. At the same time, it enables better heat removal. In contrast, on the right, we see a flat panel or tile array construct. And this form ends up lower cost because the ICs can be solder surface mounted to the back face of the panel, and this is the preferred solution for 5G base stations. The challenge here is that now the electronics for the RF circuitry needs to fit on the back face of that radiating aperture, the antenna, and the available area for the circuitry on a per element basis is nominally a half lambda at the frequency of operation. At 28 gigahertz, this amounts to about a 5 millimeter by 5 millimeter area for all that circuitry. That's a big challenge, and that frames the problem of how one can implement filters for such an array. This table summarizes the available filter technology which operate at high enough frequencies to be considered for millimeter wave applications. You can see they differ in many of their key attributes here, which are summarized across the top of this chart. First, they have to be capable of fairly tight frequency tolerances, or they're not able to yield an appropriate device to work to the performance need. Second is the resonator cues. Insertion loss of RF filters is inversely proportional to resonator cue, so higher numbers are better here. And in contrast, though, to get high Q generally means large size when the energy is stored in electromagnetic resonators. So miniaturization is an important factor with respect to the phased array, and in the relative size range, RFIC chips are capable of small size, but the resonator cues are poor. In contrast, the thin film microstrip filters on ceramics built by Knowles have very high Qs because of the dielectric properties, and they're miniaturized by virtue of those high dielectric constants. And they also achieve excellent temperature stability. Next attribute is, are they capable of integrating multiple filters into a single part? And some of them are, but they don't fit within the standard tile array construct. And that is one of the filter position 1, which is right behind the antenna element. Nor do they have the sort of element or resonator cues that are associated with getting to the desired loss levels to be used in this filter position 1. So of these, the Knowles ceramic filters are the best technology for the filters in the positions 2 and 3. The Knowles patent-pending mmWave filter solution is illustrated here. The technology enables filter array panels of up to 256 elements and resonator queues of over 1,000. It's now possible to integrate high-performance low-loss filters directly behind the antenna elements, which is the ideal architecture for interference mitigation. The inputs and outputs of the filters are on opposite faces of the panel, thus making it simple to interface to antenna elements on one surface and beamformer and IC functions on the opposite surface. Patch antenna elements could be integrated directly into the filter array panel, but the 3D nature of the technology is capable of integrating waveguide horns instead. This option provides a significant improvement in antenna gain and thus enhanced link range, which is the entire function of an array here.
The Knowles filter array solution is a paradigm shift for mmWave phased arrays. The advantages are summarized here. Current tile array and filter technologies can't integrate high-performance filters between the TR electronics and the antenna elements, known as position 1. Filters that fit in the available area don't have acceptable performance. The lack of filters at position 1 results in degraded performance of the array. Receivers are vulnerable to out-of-band transmitters, 5G and others, and adjacent channel power spillover. Transmit chains must be run at back-off conditions from peak power and efficiency to control nonlinear effects which generate radiation of adjacent channel power interfering with adjacent channel traffic. One of the more severe interference issues occurs between 5G transmit channels adjacent to bands allocated to Earth Exploration Satellite Services, or EESS. Current solutions to this interference use some of the licensed 5G bandwidth as guardband, reducing channel capacity and revenue. The Knowles filter array technology enables high-performance, low-loss precision filters to be integrated into a panel up to 256 filters with the same spacing as radiating elements required for grating lobe-free array operation. This is nominally 1/2 lambda, depending on scan angle requirements. High-performance filters in position 1 is the optimum solution for mitigation of interference issues. The filter array fabrication technology enables co-integration of 3D features such as waveguide horn antenna elements as the front face of the panel. Waveguide horn antenna elements are higher gain than patch elements by 4 dB and up to 8 dB if a plus or minus 20 degree elevation scan is adopted. This is very significant as even a 6 dB gain improvement would double base station link range and increase coverage area by 400%. Clearly, base stations with smaller array sizes and lower cost are an alternative solution for leveraging this performance enhancement. With filters between the antenna and transmitter, reduction of adjacent channel radiated power may enable less linear operation of the power amplifier, which would result in higher transmit power and efficiency and reduced waste heat issues. As you can see, this is a very significant enhancement to array applications, and we believe it is will be a real paradigm shift in how people build phased arrays. Some concluding remarks. New challenges in implementing 5G mmWave tile phased arrays has produced rapid technology innovation and new novel solutions. At Knowles, we're investing in technology development to support 5G infrastructure with industry-leading components. Finally, the Knowles Precision Devices filter array gives integrators a path forward for compact high-Q filtering at the antenna and panel form, optimum interference mitigation, and new array solutions for enhanced gain and range. We believe this will lead to new and even more novel solutions for the future systems. Thank you. We thank you for your kind attention.